Okay, today we're going to be reviewing for our mechanics physics final exam. And to do that, we're going to go through the practice exam, and you can find this on Google Classroom and follow along with us. So you'll have this on Google Classroom. I will post the link, the original exam, and I'll also post the practice exam with the answers. So if you have look at the equations we have here, general force, and these are all the equations that I will give you on the exam. So everything on this page I give you on the exam, so you don't have to memorize these. You do have to remember how to use them though. So general force first, F equals ma. Force equals mass times acceleration. Gravity is the same thing, just the force of gravity is the mass of your object times the acceleration of gravity. Next, force of friction. The force of friction is equal to the coefficient of friction. That is a number that depends on your two objects sliding together. You will not have to memorize anything, any sorts of coefficients of frictions for any object. If there's a question on friction, I will give you the coefficient of friction, and that's times the normal force to give you your force of friction. Work is a force and the displacement through that force. So for example, when you lift something up, you're pushing up against gravity. So the distance that you push against that force, that you displace through that force, is your work. And when you are doing work by lifting something up, you're giving it gravitational potential energy. And GPE is equal to mass times the acceleration of gravity times height. And you'll notice that mass times acceleration of gravity is just weight. Next, we have kinetic energy. Kinetic energy is equal to 1/2 times mass times speed squared. Now, next we have centripetal force, which is the force of, and this is a force pointing towards the center. So in circular motion, you need a force pointing towards the center to keep it going in circular motion. But let's actually start with centripetal acceleration. So centripetal acceleration is the tangential speed. So the speed, as it's moving around, it has a speed that's tangent to the circular motion. That speed squared over the radius. Next, centripetal force is just going to be mass times centripetal acceleration. So again, mass times that tangential speed divided by r. And next we have the law of gravitation. The force of gravity is going to be equal to g. G is a constant, and it's a very, very small number. I will give you the constant. If you have a question on gravity, I'll give you the constant. You do not have to memorize what G is. M1 and M2 are your different masses. Notice that you can switch them back and forth, and it doesn't matter. You're going to get the same force. So it doesn't matter if it's, for example, the Earth pulling on the moon or the moon pulling on the Earth. They're pulling with the same force. And r squared is that distance between them squared. We use r because in a circular orbit, then the radius is the distance between two objects. Next, Kepler's third law tells us p squared is d to the third. And here, p is the period of revolution, and that's in years. D is the distance in astronomical units. 1 astronomical unit is the distance from the sun to the Earth. Now, for simple harmonic motion, we've got a few equations down here. First, T for period of a pendulum is going to be equal to 2 pi times the square root of the length of the pendulum over the acceleration due to gravity. And the acceleration due to gravity will just be 10 meters per second squared. For this class, that's fine. And next, for the period of a spring, we have period equals 2 pi times the square root of mass over the spring constant. The spring constant is just a number that tells you about how the spring behaves. Again, that is something that I will give you on the exam if you have to solve any questions about the period of a spring in simple harmonic motion. And this you should remember, frequency is 1 over period, and period is 1 over frequency. Okay, let's get started. Number 1, what is the power of a machine that can perform 500 joules of work? Well, 500 joules is just, we want to get to watts, so we take 500 joules, 500 joules divided by 10 seconds, because power is the rate that we can do work, so it's work over time, giving us 50 watts. The units of power are watts, and watts are equal to joules per second, by the way. Next, an oven consumes 500 kilowatt hours of energy in order to provide 370 kilowatt hours of useful energy. What is its percent efficiency? So, percent efficiency, it's just useful energy over total energy. So, how much of that, when we plug something in the wall, we're going to draw a total amount of energy. But we really want to find out how much does that energy go where we want to. How much does it go into charging our phone or cooling the room, or this example, heating our oven. So, and it's a percent, so we have to multiply times 100 at the end. So we can take we know the useful energy is 370 kilowatt hours divided by 500 kilowatt hours, and all that times 100 is going to give us 74%. And units cancel out because kilowatt hours on the bottom and kilowatt hours on the top, those cancel out. Okay, number 4, a horse gallops around a circular arena at a constant speed. What is the direction of the centripetal force and the net force? So where are they both pointing? We said for any circular movement, there has to be a net force pointed towards the center to keep it moving in a circle. So point towards the center of the circle. If I can spell. Okay. Number 5, what is the relationship between the radius of a circle and centripetal acceleration? So if we can look up here to our centripetal acceleration equation, centripetal acceleration is equal to, we don't care about speed right now, but it's over r. So they have an inverse relationship. Okay, because centripetal acceleration scales with 1 over r, they have an inverse relationship. Okay. Next, what are the units for tangential speed? Well, this speed here should be a giveaway, because we know speed is just meters per second. So is tangential speed. So, number 7 says, some movies show a large spinning space station which simulates gravity for the people aboard. I want to know, how does that work? Why would having a big space station spinning around give you something like gravity? Well, the reason is that the spinning, or let's say the circular motion, creates a centrifugal force that pulls people into the, so I'm going to put ground here in quotes, because it's actually the inside of the ship as it's spinning around. And that acts like gravity. I'm sure you've seen this in either video games or a sci-fi movie where you have a big spinning spaceship that tries to make artificial gravity. It's due to the centrifugal force. Number 8, a water wheel has a radius of 20 meters. If the tangential velocity at the wheel's edge is 8 meters per second, what is the centripetal acceleration of the wheel? So we are going to go down to we're going to use our equation of centripetal acceleration. So centripetal acceleration, should be a C there. Centripetal acceleration is equal to the tangential velocity, which we're going to give as v squared over r. It's pretty easy to solve. We're going to do 8 meters per second, but all of that gets squared. Divide all of that by 20 meters. So we get 64 meters, 64 meters squared divided by seconds squared divided by, again, 20 meters. So what we get here is one of these meters on the top cancels out. So first let's do the number. 64 divided by 20 is going to be 3.2. And if we do meters squared over seconds squared divided by meters, one of those meters cancels out, so we get meters over seconds squared. And that's our final answer. That's the acceleration going towards the center of that water wheel. Number 9, the force of attraction between two objects of masses is directly proportional to the, and if we look at our law of gravity equation here, we can see that this force is going to be directly proportional to the product of the masses. So is directly proportional to the product of the two masses. Okay, number 10. Why don't we feel the effects of gravity from other planets and stars other than Earth. So the reason, even though they can be really big, they are so far away. And you can see in our law of gravitation, this r squared means that the distance between two objects has a really big effect. It gets counted twice, not just once, but it's the distance times the distance. So any change in distance between two objects has a huge effect. So they're so far away, and the strength of gravity is indirectly proportional to the distance between two objects. Okay. Number 11. As the Earth orbits the Sun, what is one of the focus points of its ellipse? So as planets orbit the Sun, they go in an ellipse. And if you remember Kepler's laws, you'll remember that the Sun is at one of the focus points of the ellipse. Okay, the average radius of Earth's orbit, should be a capital E, is made to be 8 times the original. How long would a year be? So if we want to do this, we can look at our handy equation up here, Kepler's third law. Period, the time it takes to go around the Sun, is equal to distance cubed. So coming back down here, period squared is equal to distance cubed. Okay. So normally the period and distance are just 1 year, 1 atomic unit. But if we make it 8 on the right side, so if we have E squared equals 8 to the third, and I don't expect you to know or to do 8 to the third that fast. I'm just going to use a calculator. So then we get P squared is equal to 512. And what's the square root of 512? I don't know. But that's why we have calculators. Plug that in, and we can round that to 22.6 years. 2.6 Earth years. Okay, so 22.6. Well, I guess in this question we were talking about the Earth, so I'll say 22.6 original Earth years. So it takes 22.6 times as long to go around the Sun. Number 13, a force causes an object to rotate counterclockwise with a moment of 85 Newton meters. Okay, counterclockwise, 85 Newton meters. A different 5 Newton force is then applied 19 meters away from the pivot to produce a clockwise motion. So I want to know what will happen. So here, we know the moment going counterclockwise, so let's find our clockwise moment. Moment is just equal to the force times the distance from the pivot. So 5 newtons times 19 meters, going to give us 95 Newton meters. And 95 Newton meters going clockwise, that's bigger than our counterclockwise moment of 85 Newton meters. So this thing is going to turn clockwise. Okay. At what point is the simple harmonic system at its max speed? It's going back and forth, and as it goes back and forth, it's a spring. It's stretched over here. It's accelerating, getting faster and faster and faster till it gets to the middle. Then it starts decelerating as it compresses the spring until it stops at the end. Then it goes back, accelerates, accelerates. So it's going the fastest in the middle before it starts to decelerate. At its relaxed point in the middle. Okay, we call that the relaxed point because there's no net force on it when it's at the relaxed point in the middle. If two waves of the same type have the same frequency, what do we know about how their amplitude relates to the energy they carry? So we know that the wave with a larger amplitude will have more energy. And the smaller wave, the wave with the smaller amplitude, will have less energy. In circular motion, tangential speed always points towards the tangent of the circle. And that might not be really clear what it means. So what I'm going to do is to open up a drawing and see if we can make it more clear by showing the tangent line at different points on showing the tangent line at different points on a circle. So if we have our circle, and let's say we're going to go clockwise around this circle. So we're going clockwise around, and at this point up here, if we were to let go of, we got rid of this thing pulling it towards the center. So for example, in class, when I let go of the string as I was letting something fly around, if I were to let go here, it would keep going straight this way. So that's where its velocity wants to take it. That's what I mean by tangential. It would go this way at this top point. It's going to go like that. Now, let's see. It keeps going down here. If I were to let go of a string, stop whatever's pulling it towards the center, let it go freely, it would go straight down. So over here, we're going to get something like that, just going straight down there. That's what tangent means. This is what's a tangent line to that circle. We're going to keep going down here till we get to the bottom, and we're going like that. If I were to let go, it would go straight like that. That's where its tangential velocity is going. And as we're going up here, it would go straight up like that. Okay, what a beautiful picture. If you want to admire my artwork, I'll put that in the answer sheet for you. We'll make it a little bit smaller. All right. Number 17. All objects have the same weight or mass, no matter where they are. So let's look at this. Weight. If we were to go to a different planet, the gravity pulling on us would be different. So our weight would change. The force pulling us down towards the ground would change. So that one can't be true. But what about mass? Mass is just based on the amount of matter we have, the amount of molecules and atoms we're made up of. That's not going to change no matter what planet we go to, or not going to change with any amounts of gravity. So we are good there. Okay. What is the shape of a planet's orbit? I think we said this one already. It is an ellipse. This is one of Kepler's laws, part of that. Now, when does a planet travel the fastest in its orbit? We can look at one of Kepler's laws again to help us out with this. So one of Kepler's laws tells us that the area that an object goes through in its orbit, if two places have an equal area, then they will take the same amount of time. Now, if you're not sure what that means, that's fine. Let's pull up let's see what Kepler meant by that with an image. All right, well, it doesn't want to show up. Okay. So here, Kepler's second law, we can see this blue area here and this blue area, they are equal. So that means this distance and this distance have to take the same amount of time. Well, both of these take 3 months, but look at this one. This one is a lot longer. So if you're going more distance in the same amount of time, that means you're going to be going faster. So when you are closer to the sun, you're going to be going faster. When you're farther from the sun, you're going to be going slower. So when does a planet travel fastest? It travels fastest when it's at the closest point in its orbit to the sun. And when does a planet travel slowest? That happens when it's at the farthest point in its orbit from the sun. Okay, number 21. Why is it easier to open a door when you push farther from the hinge? So let's think about this in terms of moments. When you push closer to the hinge, you're pushing closer to the pivot point, so your moment's going to be smaller because moment is force times the distance from the pivot. But when you're pushing farther from the hinge, you're pushing farther from the pivot point, and you're going to have a greater moment. So when you push farther from the hinge, the moment of the force increases, so it requires less force to move the door. Okay, number 22. Earth's gravitational pull on the moon is greater than, less than, or equal to the moon's pull on the Earth. Now, there are a couple of different ways of looking at this. One way we can say is, we know from Newton's laws that for every force, every push or pull, there must be an equal and opposite reaction. So if I push on the Earth is going to push back up on me with an equal and opposite reaction. If my gravity pulls on the Earth is going to pull on me with an equal and opposite reaction. Now, if we look up at our equation, we can come to the same conclusion from our law of gravitation. the force of gravity is equal to G, that's a constant, M1 times M2. So if we make M1 the Earth, M2 the Moon, then we would get how much they pull on each other. But then we could switch and make the Moon M1, the Sun M2, and we would get the same answer. It doesn't matter which one is M1, which one is M2, who is pulling on who. They're pulling with the same force. Just like what Newton's laws say, that if the moon is pulling on the Earth has to pull on the moon with an equal and opposite force. So that tells us the pull is equal. They both pull with an equal amount of force. Okay, number 23. Waves can or cannot pass through each other. So let's think about this just from what we see every day. I mean, if you go to the beach and you see waves, or at a pool, I'm sure there are plenty of times you've seen ripples cross each other, and they don't just stop, they keep moving through each other. Or some other waves we see every day, light. If I shine a flashlight, if I have light coming down from the ceiling and light coming out from my computer, they don't collide and stop. They can just pass through each other. I can see the computer screen and I can see the light, no problem. Same thing with sound. If I'm talking on one side of the room and somebody else is talking at the front of the room, those waves don't collide in the middle of the room and stop. They can just pass through each other. So someone over there can hear me, and somebody can hear someone else speaking at the same time. So waves can pass through each other. Okay, number 24. A student is riding on a carousel with a tangential speed of 6 meters per second. The carousel has a radius of 8 meters. So she is standing at the edge of the carousel and experiences a centripetal force of 300 newtons. What is the student's mass? So what we're going to use for this one is our centripetal force equation. Let's put that equation down here. Okay, so here we know the centripetal force is going to be 300 newtons. But we also know that, well, we don't know the mass, so we can leave that as m for now. But we do know the speed. And the speed squared. And we know the radius. That's 8 meters. So let's simplify this a bit. The numbers over here, we're going to get 36 divided by 8. 36 divided by 8. Well, let's put that in a calculator. That's 4.5. So we're going to have 300 newtons equals 4.5. Well, let's see what units we have. Oh, let's not forget our m. I'm going to write mass so we don't get confused here, because we also have m for meters. We have meters squared, because we squared everything in there, divided by seconds squared, divided by meters. So what that is going to do is cancel out 2 meters per second squared. Next, we have to do 300 newtons divided by 4.5 meters per second squared. So if we do 300 divided by 4.5, we get 66.7. And newtons divided by meters per second squared gives us kilograms, because 1 Newton is a kilogram meter per second squared. Okay, that's a big student. B, the student walks towards the center of the carousel until she is 4 meters away. If the motion of the carousel stays the same, what will be her tangential speed? Okay, let's look at this one. Let's look at a picture again. I think that is going to help make this a little bit more clear to see. Let's start with a circle. Okay, and this circle, we said before, if this is our carousel, it has a radius of 8 meters. Okay, but then that means if we want to find its circumference is actually going to be 16, because circumference is diameter times pi. So diameter is 2r times, I'll estimate is 3.14 meters. Okay, so that means on every rotation, she's going that distance, 16 times 3.14 meters. Now, let's see what happens when we go inside the circle. I'm trying to make it half, but my artwork's not particularly good. Let's see what happens now if we go here, and now we have a radius of 4 meters. And now, what's our circumference? Our circumference is going to be 2 pi r again. So our circumference is going to be 8 times 3.14 meters. So that means every time she does a full revolution, it's 8 times 3.14 meters. That's how far she goes. And if you notice, this is half the big circle's circumference. So it doesn't even matter what the period is, how long it takes to go around, but the period, I said, is going to stay the same. The carousel's motion isn't going to change. So the time for it to do one full revolution does not change. So if you're going half the distance in the same amount of time, that's going to halve your speed. So we should cut her speed in half. And that will tell her her current speed. Okay. And what was her speed before? 6 meters per second. So now she's going to have a speed of 3 meters per second. 6 meters per second divided by 2, because the distance she travels in one revolution is halved. So we get 3 meters per second. While on the surface of the Earth, imperfect cell has a weight of 8,000 newtons. If he moved twice as far from the center of the Earth, what is his new weight? See, how can we figure this out? Let's look at our law of gravitation equation over here. I'll bring this down for us, and let's see if we can figure out a way to use this to help us answer the question. Okay. So this is our law of gravitation. Now, I don't want to go through and plug in the mass of the Earth and the mass of imperfect cell and that constant. So what can I do? Well, I can say, well, if R equals 1, just the distance we have right now, then we know F equals 8,000 newtons. And we know that the force of gravity scales with 1 over R squared. So our force is going to be equal to 1 over, and our distance we said twice as far. So it's going to be 2 squared. And obviously that's equal to 1 over 4. So all we have to do is take 1/4 of his weight. So now it's going to be 8,000 newtons divided by 4. It's going to equal 2,000 newtons. And that will be his weight. All right. Next, he goes back to the surface of the Earth. And he digs a hole until he's halfway to the center of the Earth. What will be his new weight? So let's think about it. Do we think he's going to get heavier or lighter? Well, if we're imagining all of the weight is in the all the mass is at the center point of the Earth, we can say, well, he's getting closer to that center point. So what we can do is, again, force is 1 over R, and that's going to give us 1 divided by, well, 0.5 squared, and that's equal to 1 over 0.25, and that's just equal to 4. So our force of gravity is going to be equal to his original weight, 8,000 newtons, times 4. So his new weight is going to be 3,200 newtons. Okay, number 26. A wrench is used to turn a wrench is used to turn a screw. A force of 18 newtons is applied clockwise from the end of the wrench. The wrench is 0.6 meters long. So, what is the moment of the force? We said before, moment is just equal to force times the distance from the pivot. So, moment here equals a force of 18 newtons times 0.6 meters. I do not want to do that in my head right now. So 18 times 0.6, 10.8. Again, just like always on the exam, I will give you easy math to do, nothing too difficult. If there's anything that you would need to use a calculator for, I just give you the value. Okay, so, and our moment is going clockwise. It's important to always remember which way you're turning when you're talking about a moment. Okay, part B. If you have a 5-meter long wrench to turn counterclockwise, how much force would you need to apply to stop the screw from turning? Okay, so if we want to have zero turning motion, how do we do that? Well, we'd want the moment going clockwise to equal the moment going counterclockwise, because that way they both cancel out and we have a net moment of 0. So we want our moment clockwise to be equal to our moment counterclockwise. All right. And now we know our moment going clockwise. We said it's 10.8 Newton meters. But going counterclockwise, we don't know yet. So we know the distance from the pivot is 5 meters, but we don't know the force. So here, if we divide both sides by 5 meters, let's do that. 10.8 divided by 5. I plug that in my calculator. You get 2.16. So 2.16. Let's see what units we get. We divide both sides by 5 meters. So newtons are going to cancel out, leaving us with newtons. Meters will cancel out, leaving us with newtons. And that's good because we're looking for a force. That's what the question asked, how much force? Okay. So there we go. All right, number 27. Mr. Chris performs a demonstration using a pendulum. He finds that 30 complete oscillations on the pendulum takes 120 seconds. Part A asks us, how long is the cable that Mr. Chris is using? And tells us to use G equals 10 meters per second squared, and we can leave our answers in terms of pi. So let's find that out. I have a feeling we're going to need to use some of those equations we went over before, these simple harmonic motion equations. Let's throw this up there, although make it a bit smaller because I don't want it to take up that much space. Okay. Now, if you notice all of this, we have the period of the pendulum. That's what we're going to need. So we first need to find the period. How long does it take to do one complete oscillation? Well, it tells us it does 30 complete oscillations. Okay. And how long does that take? That takes 120 seconds. So what should we do with that 120 seconds? Let's put all this down to a new page. So let's find, what is a period? A period is the time per oscillation, and frequency is the inverse of that. Frequency is the oscillations per time. So here our units would be seconds, but for frequency, our units are going to be 1/seconds. And if you remember from earlier in the year, 1/seconds is just equal to hertz. Okay, so what we need to do is we want oscillations, how many seconds per oscillation. So we want to do 120 seconds divided by 30 oscillations, because we want to know how much time between each one, how many seconds per oscillation. So, and this is going to give us a period of 4 seconds. Okay? Makes sense. There's 30 oscillations, takes 120 seconds. So one oscillation takes 4 seconds. And if we continue with this, we can use our equation, period of a pendulum equals 2 pi, which I'm going to copy here so I don't have to worry about later. So our period of a pendulum, we already know, is 4 seconds. It's going to be equal to 2 pi. Now, here it's going to get a little tricky. I am going to write it like this. So when you're entering math stuff into a computer, this is an easy way to do exponents and roots and everything by putting everything in there. And then if you use this symbol to the 1/2, that means it's a square root. And the length of the pendulum, well, we don't know the length of the pendulum right now. And but we do know the acceleration of gravity is going to be 10 meters per second squared. Okay. And you'll notice that our length is going to be in meters in the end. So what I'm going to do right now is actually just take out that meters because, well, I feel like it. And this length is going to be in meters, cancel out the meters in there. So what we're left with there is going to be seconds to the square root. Okay. And then, so what we have to do is first, let's move over and get this whole part on its own on the right side. So we can do 8 pi s seconds equals that value over there. So 8 pi s is equal to that. And let's square both sides. Now, when you square both sides, you might have to worry about a positive and a negative result for our square root when we're squaring, but we don't have to because we're not going to have a negative pendulum length. I don't even know what that would mean. So let's square both sides. Okay, if we square both sides, that gets rid of this right here. Okay, and we can divide both sides by 10. So we get on the left side 64 times pi squared times seconds squared equals length, but we have to divide both sides by this 10 over seconds squared. What that is going to do, that's going to cancel out this boy right here. It's also going to change our 64. Let's make that a 6.4. So our length is going to be equal to 6.4 times pi okay. So the length of our pendulum is 6.4 times pi squared, and it's a length, we know it's meters, and so we said before, we wanted to get stuff to cancel out. Okay, so we've got that one. Now, B, what is the frequency of the pendulum's motion? Well, before we said that the period is 4 seconds. So period is 4 seconds. We know that frequency is just 1 over period. So that says that frequency is just going to be 1 over 4 seconds. And you can leave it as a fraction. I like to put that at 0.25 per second. And 1 over seconds gives us hertz. And there you go. So I will upload the original and the answer sheet to your practice exam onto Google Classroom. And let me know if you have any questions. Please send me a message. Things that I'd recommend studying. I know we did not get a lot of time to do the pendulum questions. I don't think it's too difficult, but maybe do some more practice with these problems. Make sure you know how to use the simple harmonic equations, simple harmonic motion equations. Another thing, make sure you know how to use this gravity equation. So I don't think there are any equations where you have to use G, M1, M2 and multiply a really long thing out. But you will have to do something like this. Like what happens if you move twice as far or 3 times as far from Earth? How much will your weight change? Same with these. So we did get a chance to do more work with centripetal force, but I know that was a while ago. So definitely make sure you refresh yourself on that and make sure you remember about circular motion, centripetal acceleration, and centripetal force. Let's see, moments are pretty easy, so make sure you don't mess anything up there. That should be free points for everything to do with moments. It's just distance from the pivot times the force, and keep track of what's going clockwise and what's going counterclockwise. Kepler's laws, you're going to want to refresh yourself on that, how things move in space, especially well, a couple things. I think you'll remember everything moves in an ellipse. You need to remember the part about when things are moving close, when things are closer to the sun in their orbit, they go faster. When they are farther in their orbit, they go slower. And I think that's it. If you forget anything about waves, you can go back to the first term. But I don't think there's anything that you don't remember. I hope you remember period and frequency, but luckily you have it in the equation sheet on this exam. And I think that's just about it. Okay, thank you for watching. I hope everybody does very well on their exams. And I'll see you on exam day. Goodbye, everybody.